Welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and today we will speak about linear models with the L1 loss. You should understand the difference between L1 and L2 regression, and you should see how the choice of the loss affects the optimization and the robustness. Let's talk a little bit about the absolute loss. You already know L2 regression, which minimizes the quadratic residuals. But we can ask ourselves if absolute residuals wouldn't seem a bit more natural, perhaps. So here you see the plot of some data. We have a regression task. So we have a continuous feature x and a continuous target variable y. The points in the two plots are the same. And on the left-hand side, you see for two sample points, for that point and for that point, the absolute difference between the true value and the predicted value, so y minus y hat, let's say. And what we do in L2 regression is that we do not only look at this absolute difference, but we take the square of this absolute difference and kind of penalize the model with this value here for this observation, and with this other value here, so the area of the square. This seems a little bit unnatural, and perhaps it would seem more natural to just use the absolute difference here. And that's exactly what the L1 loss is about. So that's also called absolute error or least absolute deviation. So if you go down here, the loss function is defined as the absolute difference between y and the predicted value, so my y minus f of x, or we can also say y minus y hat. And what you see down here is on the left hand side exactly the same thing as above, so the same points. And for these 2 points here, we have a second plot on the right hand side. So let's start with the first point. This point has an absolute residual of 1.04, and we can plot the loss function here. So this is just, well, the absolute value function. So on the x-axis we have 1.04, and on the y-axis we also have 1.04. And for the other point, the point down here, we have an absolute loss of 0.69. So the loss function is 0.69, and the residual is, of course, minus 0.69. We can have a look at the two-dimensional version of this loss and of the L2 loss. So let's think about two features. We have a feature x1 and a feature x2. And on the y-axis we have the L1 loss on the left-hand side and the L2 loss on the right-hand side. And we see that, of course, we have also this indifferentiability at 0, 0. So when the residual is 0, then the L1 loss is not differentiable in that point. So we have no analytical solution for the problem of empirical risk minimization, compared to the L2 loss, where, of course, here this is also differentiable, and of course the gradient is 0. We can have an analytical solution, but we have no analytical solution for L1 loss. Let's have a look at the estimated parameters of L1 and L2. So the point is that very often the results of L1 and L2 regression are not that different with respect to the estimated parameters. So let's have a look at some simulated data here. The data generating process is that we have an intercept of 1, and a slope of 0.5. We have one continuous feature x1, and then we have an additional noise parameter, which is just a random variable, a Gaussian random variable with mean 0 and variance 0.01. Here in this plot, you can see some points from that data generating process. And you see the estimated regression lines using L1 loss and L2 loss. So with L1 loss, we have this, with the L1 loss, we have the blue line here, and with the L2 loss, we have the orange line. And you see those lines are very different. Here, actually, the intercept is the same, just the slope is a little bit different. The slope of the L1 is a little bit slower than the slope of the L2, but it's not that different. On the right-hand side, you see the loss surfaces of intercept and slope versus the loss for L1 and L2. And you also see that it's not that different here. But, of course, there are some data situations where those two losses give different results. And here we can speak about robustness. So imagine the following data situation. So on the left-hand side, it's the same data as before. On the right-hand side, we have an outlier here. So we removed the 2 points down there on the left, and we added one outlier, which is like very different, and it's not from the same data generating process here. And you can see that the blue line, so the line resulting from the L1 loss, is really more or less the same as before. This doesn't change. But the line for the L2 loss, so the orange line, is very different. So that one here. So the L1 loss is more robust than the L2 loss. We can also give this some numbers. So if the residuals is 3 times as high, then the loss contribution is 9 times as high using the L2 loss. And with the L1 loss, this doesn't happen. Of course, if we have many outliers, then at some point, of course, also the L1 loss will pick up on that outliers. There is another difference between L1 and L2 loss, and that is regarding the optimization cost of learning the model. Let's have a look at a real-world data problem, the weather data set, where the y variable is the mean temperature. So we want to predict the mean temperature. And we compare the time we need for fitting an L1 regression and an L2 regression. So let's have a look at the plot on the left side here. All the blue boxes refer to model fits with L1 loss, all the orange boxes to model fits regarding using L2 loss. And what you see is the log of the time we needed to estimate the parameters of those models. We did this for different proportions of the data set. So for 10% of the data, for 50% of the data, and for 100%, so for the entire data set. And we did it 50 times for each of those configurations. So what you see, if you just compare all those blue boxes here, is if we have more data, then training takes more time. That's okay, I guess, somehow obvious, and it holds for both the L1 and the L2 loss. If we now compare for the same amount of data, so for 10%, for example, the time needed for L1 and L2 loss, we see that L1 loss needed more time than L2 loss, and this holds for all available proportions here. And that says that the optimization takes more time for L1 than for L2 loss. And we will not go into the details of the numerical optimization here, but it's important to know that this is true. Okay, let's have a look at 2 last points. So the estimated coefficients of the 2 models are more or less equal. So we do not have standard errors here, so we can't tell if the differences are significant here. But well, there are no real large differences between the row-wise parameter estimates here. Let's have a look at this table here, which contains the number of some losses here. And we will have a row-wise look at this table. So what you see in the first row is the total L1 loss for two different models. So for a model where we use the L1 loss for fitting and where we use the L2 loss for fitting. And what you see is that using the L1 loss, we end up with a smaller loss, a smaller outer loss, than by using the L2 loss. So this means that if the inner loss and the outer loss are aligned, of course, then we have the smallest numbers. The same holds for the second row, where we have the L2 loss as outer loss, so as evaluation metric. And then we see that if we fit using the L2 loss, the value is a little bit smaller than if we fit using the L1 loss. And again, we don't really know if this is a significant difference because we have no standard errors, but this doesn't matter too much for now because the direction is most important here. And yeah, that's it for today.